So 8.5 is called counting principles. This is baby stepping our way into more probability. Okay, so today we're going to learn how to build the number of terms in a sample set, basically. And then we'll finish this tomorrow. But 8.6 is then finding the probability that events will occur once you know that set. So there's something called the simple counting problems. This is where I could ask you, there's 10 black socks in a drawer and 5 red socks. What's the probability you'll pull a red sock? Something that's simple, easy to count, right? I would just figure out how many red socks there are over the total amount, that kind of thing. So if this says what's the probability you're going to pick an even number between the numbers 1 to 10? I don't even know why I put the 4 to 8. That doesn't make any sense to me. Ignore that. So the numbers 1 to 10 would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Which of these are even? 2, 4, 6, 8, 10. How many of them are there? 5. So if I asked you what are the odds or what's the probability of picking an even number, you would put 5 over 10. So the odds are 1/2, like flipping a coin, okay? They call them simple counting problems for a reason. So these don't require any formulas. There's nothing you have to figure out, okay? It's basic like common logic in the beginning. And then obviously it changes. So there's 2 things you need to start to look for, which is replacement and without replacement. If something has replacement, it means you begin with a fresh set every time. So for example, yesterday when I walked around with that mug and you pulled out numbers, let's say, right? If there was 34 numbers, when you walked through the door, how many possibilities were there for you to pull if you were the first person? 34. If I said, okay, put it back, and the second person walks in, how many possibilities are them? 34. That's with replacement. If it was like it actually happened where you pulled a number out and you kept it, now person number 2 comes, and how many do they have? 33. And then the next person would come, 32. That's without replacement. So you want to pay attention to things like putting back or replacing, okay? Because that will determine if the next time around you're starting with a fresh set or an altered one. So this one says, determine the number of ways in which a computer can randomly generate one or more such integers or pairs of integers from 1 through 15. So your sample set is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So how many different ways can an odd integer be picked? How many odd integers are there? 1, 2, 3, 4, 5, 6, 7, 8. How many ways can an integer that's divisible by 4 be picked? So what's divisible by 4? Is 4 divisible by 4? Yes. What would be the next? 8. Then? Any more? So how many ways can you pick? 3. So again, we're just establishing this sample set now. You're not saying what's the probability that you'll pick that number. Then it would be 3 over 15. But for now, we're just saying what is. Example 2 says 8 pieces of paper are numbered from 1 to 8 and placed in a box. One piece of paper is drawn from the box. Its number is written down and the piece of paper is returned to the box. Then a second piece of paper is drawn from the box and its number is written down. Finally, the 2 numbers are added together. In how many different ways can a sum of 12 be obtained? So if I have 1, 2, 3, 4, 5, 6, 7, 8. And somebody reaches into the bag and pulls 2 numbers out. What 2 numbers are going to result in a sum that's 12? 4 and 8. So if they pull first the 4 and then the 8, that's one way that 12 can be obtained, right? What's another way that 12 can be obtained? 5 and 7. So first they pull the 5, then they pull the 7. What else? 6 and 6. So the numbers return to the box, right? So I grab 6, but I put it back. I pull another number, and it can be 6. No, it says how many different ways, so not how many different pairs, how many different ways can it be pulled. So if I first pull out an 8 and I pull out a 4, am I reaching 12? And is it a different way than pulling out 4 and then pulling out 8? Yes, so that means you can also do 8 and 4 and 7 and 5. 6 and 6 and 6 and 6 reverse is the same, right? It's not like these are numbered, like colored pieces of paper that you would know the difference, right? That's the same piece of paper. So how many ways can the sum of 12 be obtained? 5. Questions on that one? Example 3. Almost exactly the same thing except for what? The paper is not returned. How does that have an impact on what we just found? You can't get 6 and 6, which means you can get 8 and 4, 4 and 8, 5 and 7, 7 and 5. But you can't get 6 and 6, which means this time there's only 4 options. Questions so far? Everybody okay? All right, the fundamental counting principle says if you have 2 events, and we'll call them E1 and E2, so 2 separate events, and the first, and this should be a T, and the first event can occur M1 different ways, and then after E1 has occurred, E2 can occur M2 different ways. The number of ways that the 2 events can occur is M1 times M2. So if you're doing 2 different things, you would take the amount of times the first one can happen times the amount of times the second one would happen. So how many different pairs from the English alphabet are possible? 2 separate events. Pulling the first letter, pulling the second letter. When you're grabbing a letter from the English alphabet, how many possibilities are there? 26. Now that event is finished. Second event comes into play. You're grabbing a letter from the English alphabet. How many letters are there? 26. So they're 2 separate events pulling from the same English alphabet. So I would say that this is different. You would pay attention to something if it said the English alphabet is written on pieces of paper or on cards. And the first event occurs, you take it, and you want to pay attention. Is there replacement or is there non-replacement? If there's a replacement, then it's 26 again. If there's non-replacement, that's when it comes to 25. So that's when that second event relies upon what happened in the first. Does that make sense? But a set of numbers from a random computer is going to be always the same set of numbers. The set of letters from an English alphabet is always the same. Okay? So you're going to, the hardest part to teach you on probability and all this stuff is how to read the questions because they are so different. I can't tell you exactly what to look for. You want to look for things like replacement and non-replacement, that kind of stuff. But in general, a lot of it takes your interpretation of the words. So what's 26 times 26? Is that right? No. Right? Yeah. Say again? No. 576, right? Yeah. 676. 676. Took me longer to walk over here than it did to actually multiply that out. Okay. Example 5 says a combination lock will open when the right choice of 3 numbers from 1 to 30 inclusive is selected. How many different lock combinations are possible? So there's a couple of vocab terms you want to pay attention in there. What does inclusive mean? Including 1 and 30. So how many numbers are from 1 to 30 including 1 and 30? 30. Remember, if we start at 1, it is that number. Okay? So there's 3 numbers. I've got my first number, I've got my second number, I've got my third number. How many options are there for the first number? 30. How many options are there for the second number? How many options are there for the last number? So something that said numbers couldn't repeat, then it would change, okay? But you're saying you're pulling from the same set of 30 numbers every time. So this would be 27,000 combinations. All right, this one says, in a certain state, each license plate number consists of 2 letters following by a 4-digit number. How many distinct license plate numbers can be formed? All right, so I've got 2 letters. First one is a letter A through Z. The next one is a letter A through Z. And then a 4-digit number. How many letters are there in A through Z? 26, which means there's 26 to pull from the first time. Does it say a letter can't repeat? No. So how many letters are there the second time? 26. And then I need a 4-digit number. What does that tell you about those individual numbers?
Up to 9.
They go only from what to 9? What else is a 1-digit number? 0. They go from 0 to 9. How many numbers is that? 10. So you get 10 and 10 and 10 and 10. So this was 676 and 1, 2, 3, 4 zeros. So next time you're driving in your car, you could be like, Mom, did you know that there's 6,760,000? No, just kidding. The things you think you won't use every day. Question so far? All right, permutations are next. So a permutation is determining the number of ways that n elements can be arranged in an order. So this is where order matters. Let's say I want to give you guys new seats and I want to figure them out and I want to know how many possibilities are there to rearrange you guys in order. So I've got 34 seats and this first seat, how many people can, let's say there's 34 of you. How many options do I have to fill this first seat? 34. And then I go to the next seat. Now this person's already sitting, so how many options do I have now? 33. How many options do I have now? 32. So those are each individual events, yes? To figure out what the options are, I would multiply those events out. So it would be something like 34 times 33 times 32 times 31 and so on and so forth. What does that look like? A factorial. So permutations are factorials of the number that you're trying to fill. This is where order matters. So you're going to look for words like order. Order matters. How many ways can 10 people get into a bus? How many in order? How many ways can people finish in a finish line in a certain order? How many times can it, and it will literally say order matters. And that's how you know to do permutations, okay? So how many ways can 10 objects be put in order? Would be what? So without a calculator, you are multiplying 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. If your teacher says to bring a scientific calculator and you don't bring one, oh, it's going to be fun. Okay? What you want to start doing is get comfortable with that scientific calculator. So if you have one with you, you can take it out because most of them have that factorial sign. You just got to find it. They're in different places depending on that calculator. Find the number of permutations of the following letters. A, B, C, D, E, and F.
It's the whole task when you use scientific.
Mm-hmm. How many letters are there? 6. So it is 6 factorial, which is 720. So these are questions that standardized tests love, again, because you could rewrite out A, B, C, A, B, D, A, B, E, A, B, F, then go. A, C, D, A, C, E, A, C, F. You could figure it out. It just takes you a crap ton of time. You shouldn't need to if you know something like this, okay? Questions on that one. So this is permutations, order matters, so you can't like switch it around. You're not going to count A, B, C, and C, B, A, that kind of thing. Once you use it, it's used. All right, this is where we're going to do this, and then we're going to stop for today. So permutation of elements taken at a time. So let's say I went back to that last example, and I said, find the number of permutations from that set of letters taken 2 at a time. That's when your equation changes. So it looks just like your coefficient one, where the n is on the left. That's the number of items that are in that set. The r is how many you're taking at a time. And the equation looks almost exactly like your coefficient one, right? What's different? There's no r factorial on the bottom. So it's n factorial over n minus r factorial. So I'll tell you right now that on your test, if it's a question like this, let's just say, or even a coefficient one, that I'm going to let you use your scientific calculator, but you are going to give me the formula first. So it is a show all your work kind of a scenario. What would that look like? If you want to use your calculator, use your calculator, because some of them have the permutations and some of them have the combinations on them. So a question would look something like A. Find the number of permutations of 8 horses taken 3 at a time. So what's my n?
6.
Oh, no. Number, the whole number for A. 8 horses, right? How many are you taking at a time? 3, that's your R. My formula is n factorial over n minus r factorial. So it's 8 over 8 minus 3, which is 8 over 5, and 8 times 7 times 6 times 5 factorial over 5 factorial becomes 8 times 7 times 6. Which is 336. And then really obvious, evaluate 6P2. So find on your calculator if you have a probability button, or some of you actually above your button, I think that's yours, Karina, like says NPR. That's where you would use it. Most of them you have to type the N first, then hit the NPR button, and then hit the R. So it would be 6, NPR, 2, and you get 30. So 6 factorial over 6 minus 2 factorial, which is 4 factorial, equals 6 times 5 times 4 factorial over 4 factorial. 6 times 5 is 30. Questions on anything we talked about today? So 8, obviously 8, 4. So your test is going to go all the way to 8, 6. Okay, so we've done expanding the binomials, figuring out the coefficients, and then the coefficients actually going to come back in this section as well when we finish it. But then we got into simple counting and permutations.